Hello, Nils Olav speaking. The topic for this presentation is real-time and the subject is scheduling. This is the first part of this second part containing both scheduling, synchronization and resources. So the agenda for this presentation will be mostly about scheduling. We will look into multitasking, and multitasking is general. It's a multitasking system. It can either be a general purpose operating system or a real-time operating system. When you're dealing with multitasking, you have several tasks running at the same time, and then you need some sort of service to handle these tasks, and that's what we call the scheduler. And the meaning with the scheduler is to make the maximum usage of the CPU. As it's shown here, you have a set of tasks, and you have some sort of admissions control that can handle or use the CPUs. These different tasks, they will have different states, so we'll look a little into the different states that they can have, and also the I/O performance. And at the end, I will show you the scheduling or the multitasking of the Windows operating system. So let's start with an introduction to scheduling. In a system, you have a lot of different functions, several functions, and you normally divide that into a set of tasks. You can either have a single system where you have all the tasks running at the same system, or you can have it as a distributed system where you have separate tasks running on different systems. But still, if you have tasks running on different CPUs, you still need some sort of communication or communication protocols to handle the communication between the tasks. When we're dealing with real-time system, you also have deadlines. So some of the functions will have deadlines, normally not all of them, and you try to divide it into separate tasks, the tasks that have different types of deadlines. So we try to separate it into tasks that can handle different types of deadlines. So you end up with a set of tasks without any real-time requirements and some tasks with time requirements. But the challenge is that all of these tasks should be run at the same time. And in real-time system, you also have this additional requirement that you should fulfill the deadlines. Remember the definition of real-time. It means that you should handle an unexpected event at a predefined time or in a predictable way. So that means, for example, in a system, if you have 100 events, you can either have one of the events at each time intervals, or you can have all of them together. And if you have time requirements, it doesn't matter if you have all together or one at a time. You should still be able to handle them in a predictable way. When you're dealing with a CPU can only handle one task at a time. And that's why you need these services, the scheduling services. Today you have CPUs with multi-core. That means you have several cores of the CPU. That means you can have one task for each core, but still you either have 2 or 4 or maybe 8 cores. And then the maximum task that can run at the same time is still 8. So we are using this scheduler for controlling the CPU. So only one task for each core. There are two type of schedulers. The long-term scheduler, that means normally for batch jobs. You start a job and then it will continue until the job is finished. And we have the short-term scheduler, which we are going to focus on in this course. And that's both for general purpose operating systems and real-time operating systems. So if you look at this solution, here it's what we call a macro view. For example, if the time resolution is 1 hour, it seems that all of the tasks are running at the same time. But the other way is to look at it on a CPU view. And here, for example, the time resolution can be 100 milliseconds. And then you will see that it's actually divided into small time steps. First, task number 1, then task number 2, 1, 3, 2, 1, and then 2 again. And you also notice that the length is different. So normally they are equal, but you have some that are shorter. And we will come back to. And this is the way that both real-time operating system and general purpose operating system are working. And Windows, Linux, Solaris, Unix, and so on are general purpose operating systems. So these services, the scheduling, that is handling these different tasks, that's must be a part of the kernel of the operating systems, and we will focus on the short-term schedulers. So we will have a scheduler that will handle all the tasks, and we have two different types of these short-term schedulers. Either a non-preemptive scheduler or a preemptive scheduler. The non-preemptive is the simplest one, not the one that are used most, but just so you should know about it. So if you look at it, it's this one. It means that you have the scheduler will start what the tasks that it means that should run. And then when the task is finished, it will handle a control back to the scheduler, which will figure out which tasks to run next. The disadvantage here is that as long as the task 1 has control of the CPU, it can use the CPU as long as it wants. So it's up to how you are actually designing the software to be sure that you will give the control back and that you will share the CPU with all the other tasks. The other scheduler is a preemptive scheduler. Instead of giving the control back, it has a timer that is controlling one of the interrupts, normally the priority with the highest, or the interrupt with the highest priority. So we have timer ticks sending interrupts to the CPU, and when the CPU is aborted by an interrupt, it will always start the scheduler. And then the scheduler will figure out which task to run next, and then transfer the control to the task, and then the task will run until it's aborted by the next timer interrupt. So we will focus on the preemptive scheduler, which is normal for both general purpose operating system and real-time operating systems. So it's using a timer and this high priority interrupt. So we have a high priority interrupt service routines, which is the scheduler, and it's running at fixed time intervals. For example, on the PC platform, it will run at every 18.2 milliseconds. So that means it will run more than 50 times each second. The scheduler will be in control, figure out which task to run, and then start that task. So we have this context, which I explained in the introduction. So the scheduler, we switch the context. It will first save the CPU registers, the program counter, and the stack segment for the running task. Figure out which one to run next, load the new CPU registers, PC, and the stack segment for the new task, and then give the control to the task. And then the task will run until it's aborted by this timer. And then it's important to understand that these tasks can be aborted at any time because you don't know when you will have the next timer. And the scheduler, it has some sort of policies or strategies to figure out which one to run next. Either time, event, or priority. Priority is the most used, but there exist also other priorities. And the reason is try to utilize the CPU, have a highest possible throughput and response time of the tasks. So you have several tasks. The tasks can be aborted at any time, so that any task will have any of these 4 states. You start at ready, and then when you have a high enough priority, the scheduler will switch you to running. That means you are the one that are using the CPU, and when it's aborted by the timer interrupt, you will put back to the ready state. If you need some sort of resources and the resource is occupied, you can go to the waiting state. And then when the resource is available, you will go back to ready and then use the CPU when you have a high enough priority or the scheduler decided that you can use it again. The last state is offline. Offline means that you have not been loaded into memory. Here in another diagram, they're calling it offline is called suspended. Waiting is called blocked. But still, you have ready, running, and then if you're using some sort of resources that are occupied, you are going to be blocked and back to ready, and then you can run next. So the states are offline. That means you are not loaded into memory yet. You are in a secondary memory device, disk, or somewhere out of the reach of the CPU, but it can be loaded into memory, and then it's ready. Then when actually using the CPU, you are in the running state, either one, or you can have several tasks if you have a multi. And waiting, that means you are waiting for some sort of resources, and it's checked by the scheduler. And when you are dealing with multitasking, you should always let the scheduler handle the waiting. Not try to to handle the waiting in the task itself. The scheduler are also using a set of queues to handle these different task states. So it has a set of queues or tables to maintain the state of each task. And it's one queue for each of the state. You have a wait queue, a ready queue, and a run queue. And you're using what we call a process ID or a task ID. PID or these tables will also contain the context information, so everything about the task is saved in. So the scheduler, it will be started by the interrupt. It will save the current context. It will first check the wait queue to figure out if some of the resources are available. In that case, it will move the state from wait to ready. Then it goes through the ready to check for the one that has the highest priority for run. And then it will load the new context information into the system and then start that task based on the information from it. So we have different strategies for the scheduler. They are always trying to make the best use of the CPU, as the CPU is the most important resource in a multitasking operating system or also in a real-time operating system. Different strategies are, for example, round robin. Here, they're just running task for task for task. You can use priority. That means the one with the highest priority has to run first. We also have shortest job first. That means the one that is using the CPU for the shortest time will run first. Also first in, first out, or first come, first served. So some operating system, you are locked to a specific strategy, or you can also configure it. But again, the scheduler is overloading or using extra resources from the system, so it should be as simple or as short as possible. Remember that in a PC-based system, the total time step is 18.2 milliseconds. And then the scheduler should be as short as possible. So this 18.2 milliseconds should be utilized by the task, actually the tasks. Not little about I/O performance. We will start with interrupts. We have this timer interrupt. What is actually happening? You have a task that is running. When you got an interrupt is an electrical signal, a hardware signal to the CPU. The CPU will figure out the type of interrupt. Normally they have different priorities. And if it's a valid interrupt, it will make a context switch. This task that is running, it will be stored and it will start what we call an interrupt service routine. And then the service routine will run, and when it's finished, it will have a context switch back and the task will continue running. And we also have this interrupt latency, which is a time from you have an interrupt until the interrupt service routine is running. And the scheduler is a type of interrupt service routine. So we have an interrupt and the interrupt service routine or the scheduler will run. But instead of going back to the task that was running, the scheduler will modify the context switch, so it will switch to the task that should be running after the scheduler is finished. So interrupts are controlled by the scheduler. You can have external events from the process. That's mainly digital signals, on-off signals, that are triggering some sort of interrupts. But as long as you have the highest priority for the scheduler, that means if you have a lower priority, they will not get in the way of the scheduler. You can also have internal events. For example, on microcontrollers, you can have duck conversion and so on, also giving internal events. So the interrupt consists of a hardware signal starting some sort of interrupt service routine. When it's dealing with reading values, external values, we normally use interrupts for digital signals, and we use polling for analog signals. And you see the difference here. If you have polling, that means you have fixed intervals. You have a separate task that will deal with reading the polling value. And it's waste of time if you have a digital signal, because here you have a digital signal. You just wait for the change digital level. And then you have an interrupt and you know that now the signal has changed. But dealing with analog values, you need to read them at fixed values, at least the sampling values. Then I will use the Windows Task Manager as an example of the scheduler. We will look a little into Windows multitasking system. This Task Manager you can start up in 3 different ways. Either use a left Control and Shift button and Escape button, all 3 together, or you can use the Windows key together with the R and then type taskmanager.exe, Or you can press Ctrl and Alt and Delete and select Task Manager from the menu. I normally use Ctrl, Shift and Escape. It's very easy when you are dealing, especially when you are doing development. If you want to abort a process or want to see how the process is running, just use Ctrl, Shift and Escape and you have the Task Manager up and running. So let's look at the Task Manager. You have, when you start up, it will look something like this. This is for Windows T. It's a little different for different Windows versions. But you have a menu and you have this menu bar, these tab folders. The default is processes, just showing the processes that are running. You can have performance. The one that we are going to look at is the details. So let's look at the scheduler. So here we have the Task Manager for Windows. It's selected details, and then you see you have a set of tasks running. This scroller bar shows the number of them. This is just an ordinary Windows system, so you see you have a lot of tasks running. You have the process ID, the status, how much CPU it is using, how much memory, the base priority, threads, and so on. If you go into one of them and click on that, you see you can change the priority if you want. You can set it lower or higher. Also, you can end the task. If you are doing development and there's something wrong and you just want to quit it, then you can end the task this way. You can also have more information by clicking on a column, select columns, and then you can select more information. The one that I'm showing is not the default. I have added some additional information. So it's a lot of other information. For example, if you want to debug I/O operations, you can also see that if you click here, for example, it will be sorted by the one that are using the CPU most. It's idle, system idle, or screen customatic. You can use the name, then it's sorted alphabetically, and so on. So this, by selecting details, you will have some additional information about the task running on Windows. Conclusion is, we have looked into multitasking. Multitasking means that you have several tasks, showing here, running at the same time. And since you have several tasks, only one can use the CPU at a time, so we need some sort of services called a scheduler. Two different types of scheduler, either emptive or preemptive scheduler, where preemptive scheduler is the one that is used most. The scheduler is then controlled by a timer. So at fixed time intervals, the scheduler will run and abort any task at any time. So you don't know in which operation the tasks. That means you will have several states, mainly the ready state, the run state, or the waiting state. Ready is when you're ready to use the CPU. The running is the one that is actually using the CPU, and waiting is if you're waiting for some sort of result. The scheduler is using a set of queues and also strategies to figure out which one to run. And also look a little into I/O performance, the difference between using interrupt and polling, and I showed how it can be done or used by the Windows